Okay, hi, so this is Melanie again, and this is a video on KSP, Ka, and Kb. So KSP, Ka, and Kb are all used to measure the concentration of ions in from a slightly soluble solution during equilibrium. So KSP measures, or it's also known as the solubility product, and it measures the solubility of a slightly soluble ionic salt. Ka measures the solubility or ionization of a weak acid, and Kb does that for a base. And so in this first reaction here, we have a KSP. So it's a salt which is slightly soluble ionizing. And so the KSP will represent how much of that ionizes. And it's the same thing as KEQ, where it's products over reactants. And so for this one, it would be the concentration of Ag plus to the second power, and then the concentration of S2 minus. And then because Ag2S is a solid, it's not included in the KSP reactions because solids are not included for concentration. Below, this is the ionization of a weak acid. And so over here you can see that the HF breaks down to H plus and F minus, and then the H plus will form hydronium ions, which are highlighted in yellow over here. And so the Ka for this reaction would be the concentration of H plus multiplied by the concentration of F minus over the concentration of HF. And in this one we do include, the HF because it is an aqueous solution, and so it will be included in the Ka expression. Okay, so most of the time when you're given a KSP, Ka, or Kb problem, you'll get a chart with KSP, Ka, or Kb values, which you see here. So this is the one for KSP, and here's the one for Ka, and you just look through and find the value of the substance that you're given. So now on to some practice problems. Here's one for KSP. So find the equilibrium concentration of ions present in a saturated solution of calcium fluoride and its molar solubility. The KSP for CaF2 is 3.5 times 10 to the negative 11th. So first, molar solubility is the amount in moles of a salt dissolved to make a 1 liter saturated solution. And so that over here is denoted in the change box. So it's pretty much just how much dissolves in a 1 liter saturated solution. So now to start the problem, at the beginning, or in the initial box, we don't have any Ca2 plus or F minus ions. So we're going to start by putting zeros there. Also, because CaF2 is a solid, that will not be included in our KSP expression, so we can just kind of like cross those boxes out. Okay, and so now to calculate the change box, we don't know what we have, so we're just going to use a variable, which would be x. And so we're going to do minus x here, plus x here, and plus 2x here because we take into account the stoichiometric coefficient. And then again at equilibrium, we know we've added x and 2x. So now on to the calculations for this. 1 second. So in order to do the KSP expression, it's going to be the same thing as KEQ, or that we saw on the first slide, but it's going to be KSP equals the concentration of Ca2 plus multiplied by the concentration of F minus squared, because again we take into account the stoichiometric coefficients. And in the problem we saw that that was given, and it was 3.5 times 10 to the negative 11th. So now we just have to plug in what we have, and so we in the equilibrium row we figured out that there's x amount of Ca2 plus at equilibrium and 2x of F minus. And so we're just going to plug those in for the concentrations down here. So we're going to get the KSP equals x times 2x squared equals 3.5 times 10 to the negative 11. So now we just have to multiply these together, so we get 4x to the third equals 3.5 times 10 to the negative 11. And so now all we have to do is solve for x. So we'll start by dividing by 4, so that's x to the third equals, here, oops, so 3.5 times 10 to the negative 11th, divide that by 4, and now we're going to take the cube root of that. Okay, so after we divide 3.5 times 10 to the negative 11th by 4, we're just going to take the cube root of that, which can also be done by raising it to the negative, or to the 1/3 power. 1/3, there you go. And for that, we get, so x equals 2.0606 times 10 to the negative 4th. And so from there, if you look back at our ICE table, we have the x represents the concentration of the calcium ion, and so that would be, so the concentration of Ca2 plus equals 2.1 times 10 to the negative 4th molar when you take into account sig figs. And so the concentration of F minus, we're just going to multiply by 2, and so that's going to be the concentration of F minus equals 4.1 times 10 to the negative 4th, again taking into account sig figs. And to find the molar solubility, that was just the change for the reactants, and so that was just represented by x, and so that would be the same 2.1 times 10 to the negative 4th molar. Okay, so now on to a Ka example problem. So calculate the equilibrium concentration of ions present in a 0.2 molar HF solution and the percent ionization. The Ka for HF is 7.2 times 10 to the negative 4th. And so from this given information, you're able to figure out that the initial concentration of HF is 0.20 molar. And again, at the initial, we have no H or no F. So from there, we're just going to plug in our variables, and so we're going to subtract X amount of this, add X here, and add X here. And so at equilibrium, we'll have 0.2 minus X, X, and X. And so now on to actually solving the problem. So now that we have our ICE table, we can actually set up the expression, which is going to be the same thing. So it's going to be the Ka equals the concentration of H plus multiplied by the concentration of F minus over the concentration of HF. And again, HF is aqueous, and so it has to be included in the Ka expression, whereas for KSP it was a solid, so it didn't need to, and it's just products over reactants raised to stoichiometric coefficients. So now comes time to plug stuff in. So we were given the Ka, which was 7.2 times 10 to the negative 4th, and then equals X times X over 0.2 minus X. But however, for this, the X in the denominator is negligible because it's less than 10% ionization, and so you're able to just do 7.2 times 10 to the negative 4th equals X squared over 0.2. And by removing this X from our equation, we're able to save a lot of time and effort because we don't have to do like a long quadratic equation, which takes a lot more time and is not as fun. So just doing this math now, all we have to do is again plug it into our calculator. So you have 7.2 times 10 to the negative 4th, multiply that by 0.2, and now we're just going to take the square root of this, and then that's okay. So all you do is plug it into your calculator now, and so it's going to be 7.2 times 10 to the negative 4th, and then we're going to multiply that by 0.2 and take the square root of that answer, which gives us X equals 0.012, And back to our ice table, the concentration of H plus equals 0.012, which equals 1.2 times 10 to the negative second. And the same thing goes for F because they're both represented by X. And so that will be 1.2 times 10 to the negative second as well. And so that is what that problem is asking us for, and there's the solution. Okay, so last problem, onto a KB problem. So this is the problem. Calculate the KB and equilibrium concentrations of ions present in a 0.10 molar ammonium solution with 1.34% ionization. So from this, as we can see, we're looking for the KB and the equilibrium concentration of ions. So going back to our problem, we need to find what we can fill in our icebox. And so we see that we have 0.10 molar of NH3 initially. And we also know that we have none of either of the products. And so now when it comes to calculating the change, we know that 1.34% of the NH3 ionizes, and so 1.34% is represented by 0.0134 as a decimal, and now we're just going to multiply that by 0.1 because it's that percent of the 0.1 that we had. And so you're going to get 0.00134, but that's negative because that's turning into an ion. And then over here, because they all have a stoichiometric coefficient of 1, it's just going to be plus 0.00134 and plus 0.00134. So now at the equilibrium, we have 0.10 minus 0.00134, and then 0.00134 and 0.00134. So now that our ice table is filled out, we can go into creating our expression, which is the same thing as we had before for both Ka and KSP. It's just products over reactants raised to stoichiometric coefficients. So for that, it would look like Kb equals the concentration of NH4 plus multiplied by the concentration of OH minus over the concentration of NH3. And so now all we have to do is plug in what we know from our icebox. And so again, with Ka and Kb, you're looking at the equilibrium part of the icebox. And so for that, we have Kb equals the not the concentration anymore, we're plugging stuff in. It's going to be 0.00134 squared because those two are both the same over 0.10 minus 0.00134. And so now we just have to plug that into our calculators and solve. And so, so it's going to look like this, 0.00134 squared over, that would be over 0.10 minus 0.00134. And from that, we're going to get the Kb is equal to 1.8 times 10 to the negative fifth, which is the answer. And then also the problem had asked you to solve for the equilibrium concentration of ions, and you did that by looking, by calculating the change, and those two answers will be right there. And so the concentration of NH4 plus equals the concentration of OH minus, because again, they're equal because of the stoichiometric coefficients, and those are both going to equal 1.34 times 10 to the negative third. Okay, oops, sorry, there you go. And that is pretty much Ka, Kb, and KSP. So thank you.